Let's understand determinant in this video. Have you ever wondered how we tell if a matrix can be reversed or solved easily? By a single number, the determinant helps with that. A submatrix is what you get when you delete some rows or some columns from a matrix. It is just a smaller matrix inside the big one. For a 1 by 1 matrix, the determinant is the single number itself. For example, if the matrix is -3, the determinant is -3. For a 2 by 2 matrix with entries AB in the first row and CD in the second row, the determinant is A times D minus B times C. Let us do a quick 2 by 2 example. Question number 1 asks, find the determinant of the matrix with first row 2 and 3 and second row 5 and 7. We compute 2 times 7, which is 14, then 3 times 5, which is 15. Subtracting gives 14 minus 15 equals -1, so the determinant is -1. Now we meet two new ideas for bigger matrices, a minor and a cofactor, and I will explain each simply. The minor of the element in row I and column J is the determinant of the matrix left after deleting that row and that column. The cofactor of that element is -1 raised to the power I plus j times the minor, so the sign depends on the position. Using cofactors, we get the Laplace expansion, which is a way to get a big determinant by expanding along any row or any column. For example, the determinant equals A11 times its cofactor plus A12 times its cofactor and so on along the first row. This means we can reduce a big determinant to many smaller determinants, one step at a time, like working on a blackboard slowly. Now some useful properties that make life easier. Property 1 says the determinant of a matrix equals the determinant of its transpose. Property 2 says that if two rows or two columns are swapped, the sign of the determinant flips to its negative. Property 3 says that if two rows or two columns are identical, the determinant is 0 because swapping does not change it but sign changes. Property 4 says if we multiply all entries of one row or one column by k, the whole determinant is multiplied by k. Property 5 is linearity, which means if a row is a sum of two vectors, the determinant splits into a sum of two determinants with that row replaced. Property 6 says adding a multiple of one row to another row does not change the determinant. And this is the main row operation we use. Property 7 is about polynomials. If a determinant as a function of x is 0 at x equals a, then x minus a is a factor of that determinant. Let us solve a typical example from the notes. Question number 2 asks to find the determinant of a special n by n matrix where many entries repeat in rows and columns. The trick is to perform row operations, subtract the first row from other rows, so the other rows become proportional or develop zeros, which makes the determinant 0. Therefore, the determinant of that special matrix is 0 because we created dependent rows with simple row subtractions. Another classic example is the Vandermonde type determinant in A, B, C and D, and we will show it factors into products like A minus B and so on. Question number 3 asks, prove the determinant equals the product of terms A minus B, A minus C, A minus D, B minus C, B minus D and C minus D. We apply the row operations. Second row becomes second row minus first row. Third row becomes third row minus first row, and simplify step by step. After these steps, we can factor out terms like A minus B and A minus C from rows, and the remaining small determinant simplifies to give the final product. So the determinant equals the product of those pairwise differences, that is the Vandermonde product, and it becomes 0 when any two variables are equal. One more solved idea. Show D equals the product quantity x minus y times y minus z times z minus x times plus y plus z. We note if x equals y, then two columns become identical. So D is 0. So x minus y is a factor. And similarly, the other two differences are factors. Since D is homogeneous of degree 4, one more linear factor remains. So D equals k times the product of those three differences and one more linear term. Plugging in values x equals 0, y equals 1, z equals 2, we compute the determinant value and find k equals 1, so the formula holds. Also, a helpful multiplicative property is determinant of AB equals determinant of A times determinant of B for square matrices of same order. Let us check that with a 2 by 2 numeric example. Take A equals the matrix 1, 2, 3, 4 and B equals the matrix 0, 1, 1, 0. Compute determinant of A as 1 times 4 minus 2 times 3 equals 4 minus 6 equals minus 2 and determinant of B as 0 times 0 minus 1 times 1 equals minus 1. Multiply A and B to get AB equals 2, 1 in the first row and 4, 3 in the second row. Its determinant equals 2 times 3 minus 1 times 4 equals 6 minus 4 equals 2. Now, determinant of A times determinant of B equals minus 2 times minus 1 equals 2, which matches determinant of AB and confirms the rule. So what do we learn from this? Determinants give a single number that captures row dependence and scaling. And there are clear rules to compute and simplify them. Let us quickly remember submatrix, minor, cofactor, Laplace expansion, key properties and the multiplicative rule, and practice row operations to simplify examples. Thank you for listening. Keep practicing these steps slowly and do explore more worked examples and notes on EduRev to build confidence. You are doing well.